Is everybody ready? So today's recitation is on exceptional control flow. So you just had your midterms last week, and now the next lab is out, Shell Lab. And Shell Lab will require you to understand things about exceptions, exception handling, exceptional control flow, and also stuff about I/O redirection. You'll be writing your own little shell. So there's a lot of slides in this. I'm going to go through them kind of fast so that we have time to talk about Shell Lab at the end. But if we get to a slide and it's something that you don't understand or you want me to slow down and re-explain a bit, just let me know and I will go over it in more detail. But you should have seen most of this in lecture already. So, okay, yeah. So midterm scores are on AutoLab now. There was a period of time where we had released them but not released them, so everyone had zeros. So you can check again and your actual score should be up now. You can view your exam if you want to review how you did in office hours. Just in Wien 5207, our normal office hours room. We'll be able to let you look over the results again and what the correct answers were if you missed anything. And if you want to make a regrade request, if you feel that you should have gotten credit for an answer and it didn't give you credit for it, or that the credit it gave you was wrong in some way, then you can submit a hard copy written request to Professor O'Halloran. You should do that this week. You should, if you go to his office and he's not there, you can slip it under his door. The process for that is outlined in the course syllabus, too, if you want to read it there. But it needs to be a hard copy written request, and that is even if you've already emailed the staff list or if you talk to a TA after your exam, you should still make sure you do that so that we are able to process your request. Okay, so up until now, we've had two mechanisms for changing control flow in a program. You've seen this in your bomb lab and your attack lab. You can do jumps to jump to a different part of the code. That's how for loops, while loops ended up turning into jumps with conditions. And then you also had function calls and returns from functions, which were another mechanism of control flow. And those react to changes in your program's state. So the jumps are either an unconditional jump, or it's a jump based on some condition of the program state, and the call and return in the same way they are controlled by as the program executes and its state changes, it will go into a branch that has a call or a return and do that. But we want to be able to do more than that. In order to have a complete system, we need to be able to react to changes in system state. So a computer system has more than just programs in it. It also has hardware devices that might have changes. You might be reading or writing to a disk. You might be getting information from a network adapter, and you need to be able to react to those changes because those are external to your program. You might have an instruction that when it executes, it causes something bad to happen, like you divide by 0 or you try to access a piece of memory that's not valid for being accessed. That's something that you need to be able to react to. The user might send signals by keyboard commands, so they might hit Control-C or Control-Z, which send different signals. You might have system timers, and so you need to be able to have mechanisms for handling these exceptional cases, these exceptions in the control flow. So there's a couple different classes of these. So there's asynchronous exceptions, which are called interrupts, and these are caused by events that are external to the processor. So this is stuff like I/O. If you're reading or writing to a disk, it can send you asynchronous exceptions. If someone hits the reset button on the computer or Control-Alt-Delete on like a Windows PC, that sends an asynchronous exception that needs to be handled. There's the synchronous exceptions. So the synchronous exceptions happen as a result of executing a particular instruction. The asynchronous exceptions, they happen whenever. You can't look at the assembly code and say there might be an asynchronous exception here because they just happen wherever the hardware device happens to send it in. The synchronous exceptions happen because of a particular instruction being executed, which has a certain result. So there's a couple different kinds of these. There's traps. So a trap is an intentional exception that we cause to happen. So for example, system calls. We want to be able to make calls to certain system functions that allow the kernel to do different management of the system that's more than just what our program does. So this is stuff you should have seen in class, like when we do a fork or an exec. The kernel needs to be able to set some stuff up. And so we make a system call to those functions, and that actually takes control out of our program for a bit, lets the kernel do its thing, and then we return to exactly where we were before. We also can handle breakpoints this way. So the way GDB is able to set breakpoints is it makes it so that every function call ends up being a trap, and then it handles that trap by pausing execution of the program, letting you do what you want in GDB, and then it will continue it when you choose to continue. Then there's some special instructions that can cause it, but then in the end, after the trap, we just return straight to the next instruction and continue executing like we were before, which is, this is the idea of it being synchronous. And then there's also faults. So faults are things that we didn't intend to happen. We weren't necessarily expecting it to happen, but we might be able to recover from it anyway. We might be able to keep going. And so some examples of this are page faults. So you'll learn more about the virtual memory system later. But what has to happen when we access the memory is it needs to be loaded up by the virtual memory system as something that we can access. And the first time we access some particular memory, the virtual memory system doesn't have it ready yet. And so there will be something called a page fault, and the system will go ahead and make sure that that memory can be used. And then we continue on executing, and everything's OK. And you'll learn more about the details of that later. But that's something that needs to happen. It's sort of like the same mechanism as a cache miss. It's not in there. You have to load it up, and then you keep going. But then we have other things like protection faults. So you could see this in the form of a seg fault if you try dereferencing null. Null is an address that you're not allowed to write to. And so what will happen is you'll get a fault, and you can't recover from that. Your program is going to have to stop because there's nothing you can do. You might also see this a floating point exception. So if you divide by 0, that causes a floating point exception. Or if you mod by 0, that causes a floating point exception. And so then you can't really recover from that. You'll get a fault. And then what you can do, so what happens is if the fault was recoverable, so in the case of a page fault, it re-executes that same instruction. So if you tried to load a memory address and there was a page fault, then, of course, once you've got that page loaded up as it's supposed to be, you want to re-execute the same instruction so that that thing actually happened, because the first time it wasn't able to do it. Otherwise, if you're not able to recover from it, your program will just abort. So a seg fault or a floating point exception will typically, you'll just see your program stop running. And then there's the unintentional, unrecoverable errors that are aborts. This is stuff like if your RAM gets corrupted, there might be a parity error. So the RAM is sort of keeping track of some information to make sure that it's staying in a correct state. And if it notices that something got corrupted, well, there's nothing you can do about that. You can't really get it back, so it will just abort. You don't see these too often. I guess you could maybe make them happen if you're like physically messing with your computer and like taking the RAM out while it's running or something. I don't know. These aren't things that you cause by bad programming. They're sort of things that happen when the hardware goes wrong. So you don't see them much because usually hardware is pretty good. But if you have bad hardware, you might see these. So, okay, so what's a program? So we have, in our system, we have programs. So the program is, the executable binary file that we've compiled. And, it's written according to a specific specification. So in the case of Linux executables, it's a format called ELF. So we've got the specification. It tells us, it has the instructions in it. It tells us what the program is supposed to do. The machine can read it. And it's just this static binary file. The program itself is just this static sequence of bytes. But then we actually, need to execute it. So then we have a process, which is an instance of a running program. And then the process in addition to having that static program associated with it, needs to have a sense of its control flow, where it is in the execution of this program. It needs to have its own address space, the memory locations that it can access, and what's in them. Now there's an abstraction of virtual address spaces. So this is something you'll talk about later. You don't need to know the details about it now. But essentially, the computer makes it so that every program can pretend it has access to all of memory and nothing else is using it. So when you have these addresses, if you're running two programs at the same time, you might see something like they're both accessing the same address and reading to and writing from it, or reading from and writing to it. But it's not actually the same address. Underneath, the machine is actually mapping these to real physical addresses so that everyone has their own unique space. But everyone can pretend that they have everything. And then you can have multiple processes running at the same time through concurrency. Okay, so let's see. So 4 basic states of processes. So processes can be running. So it's the one that's actually executing instructions on the CPU right now. The number of processes you can have running at once is bounded by the number of CPU cores you have. So now that we have multi-core computers, we can actually have 4 processes, if you have a quad-core computer, running literally at the same time. But then if we, if we have 8 programs open, only 4 will be running at any given time at most. And then the rest might be, runnable. They're waiting to be running, and they're just going to switch between them. They might be blocked, waiting for input or some event to happen. And then, so they're not runnable when they're in the blocked state. And then there's also the state of zombies. So I think did you talk about zombies in class? Yes? Yes? Okay. Yeah, so then there's the zombie state. So when a process terminates, it becomes a zombie until it gets reaped. And so the process sort of stays around so that the process that called it, its parent, can take a peek at why it exited if it cares, and then it should get reaped. And it'll cease to exist as a process. So, okay, so there's some basic control functions that we have, and these are things that you'll be using during Shell Lab. So we've got forking, execing, exiting, and waiting. We have these are standard Unix processes. We have some version of these on anything that's Unix or Unix-like. And then we also have wrappers for these, error handling wrappers for these that are the same name except with a capital letter provided by the csapp.h file, which is on the website. So what do these do? So we have fork. Fork takes no arguments. It returns an int, except it's interesting because it actually returns twice when you call it once. Because what it does is it creates a new child process that's identical to the process that called it. So essentially it takes the process that you currently have and it clones it, and then it lets both of them run at the same time. So the entire state is duplicated. All of the memory becomes unique. So now, if we change a pointer in the parent, that change is not reflected in the child. They have unique memory, unique address spaces. The registers at their current, in their current state are duplicated, except for the return value is going to be different based on whether it's the parent returning or the child returning. That's how you can tell the difference between the two, is the return value. And then file descriptors. So have you talked about file descriptors yet in class? Yes? No? Yes? Okay. So the file descriptors are unique. So if you change those around, that's not reflected in both. But the actual files that they're pointing to are shared, of course. So it's not making a copy of the files on disk. If you're modifying the same file from both the parent and the child, it is still one file on disk. And so you get equal but two distinct states. And then, of course, it returns twice because the parent returns and the child returns from this fork, because they're both able to go off and do their thing. And then you can use the return value to do the control flow of making the child do one thing and the parent do something else. So here's an example of fork. So it returns 0 to the child process, and it returns the child's process ID to the parent process. So if the parent wants to keep track of what happened to the child, it now has an ID to keep track of it. So we have something here. We do a fork, and then we're doing a conditional based on the return value of the fork. So if it's 0, then we know it's the child. So then the child would print hello from child. And if it's anything else, then it's the parent. And so we print hello from parent. And so this way, both will print based on which one they are. And what we know is that actually this can happen in either order. The order that they return in child or parent is whatever happens. The system gets to decide that arbitrarily, and so we could see these two print out in either order. And that's something you're going to have to think about while you do your shell lab, is making sure that things are not happening out of order in a way that will mess up your program. So then another thing we have is exec. So this is the second class of system calls. So exec replaces the current process's state and context with a different one. So essentially it turns one program into another. If we're running a program and we want to just say load up another and now start running this thing instead, that's what exec does. And so we never return if it executes successfully. So we call it once. Fork, we called it once and it returned twice. Exec, as long as it works, we call once and return 0 times. If it fails, we'll get an error code. And so we will get a return. But otherwise, we never return from the exec because now we're running a different process. Essentially, well, we're running a different program. It's in the same process. But we're running a different program, and that's the program that's going to execute. So so exec VE is going to be the one that will be useful to you for shell lab. And this is sort of how, you're writing a shell. The shell takes in a program on the command line, and then it has to run it. So sort of the idea is that you can fork off a child, and then the child can exec this program, and that's how you get the program to run. And then the parent remains as a shell. And so this way you can, every time you run a program, you get a new process that then turns into what that program is to make it run. This is sort of what you'll be doing. Then there's another one, exit. Exit is pretty easy. You give it a status, which sort of can be used to indicate what sort of error it was. 0 is typically uses the error code for there wasn't an error, everything was okay. And when you exit, what it does is it causes the program to terminate and reduces the process into a zombie state. And then it frees all the resources, it frees whatever memory, whatever file descriptors, becomes a zombie, and then it'll just sit around until it gets reaped. So the parent process can check what that exit code was, if it wants to do something based on it, and then reap it. Or if the parent has already died before the child, there's the program that's sort of the base program that everything is a descendant of, which is called the init, will handle reaping it, so that it doesn't just sit around forever. And when this happens, a signal is sent to the parent so that the parent can use that signal to know that it has something to check. And then the last one is wait. So wait suspends a process until one of its children terminates. So exit sends the signal to the parent when the child terminates. Wait is how the parent can sit around and wait for that signal to happen and then do something based on it. So wait will return a process ID based on the process that got terminated. And then you can do something with it. So there's different variants of this, and you can check the man page. The one that'll be useful to you for shell lab is wait PID. Yes?
What's the point of having a manual read? Why can't, is it beneficial? Can you just terminate? Why can't you just terminate and read?
So why can't you just...
I mean, why can't you... why is that just one thing?
Why can't you just, when it dies, it's dead and you don't have to do anything more? So the parent might want to be able to check what this exit status was. So say you have a parent that's forking off children, it might want to be able to do some error handling if one of them exited in a particular way, or modify its state to know that, hey, a child exited. I now know that I don't have this child around anymore. And so we just keep the zombie around. When the process is closed, even before it's reaped, it already frees the memory and everything associated with it. But it just sticks around because it needs something to have that exit status sitting there until it gets that gets handled and we know we don't need that anymore.
Why do we need to reap it if it takes care of?
So init will take care of it if the parent is already dead. But if the parent is still alive, then the parent might want to do something with it. So the parent, gets its chance to do something, and then it'll die. Okay. So here's this example. Yeah, we saw this before. This is a variant of the example that we saw with fork. So this is an important thing. Fork will give you the child and the parent in either order. You're not guaranteed that you're going to get the one order or the other. So when we execute this code, we can see that it might print child first and then parent. If the child was the first one to return, it might print parent and then child. So a question for you to think about is, how do we get the child to always print first?
Just wait till the...
Yeah, we can use our other system calls like wait in order to make it so that the parent won't print out until it's received the information that the child has terminated, so then the child has already printed, and then the parent can go ahead and print. So that's the sort of stuff you'll need to be doing in Shell Lab, is just making sure, and here it is. We just wait till the child terminates, and then the parent can inspect the exit status if it wants, and then it can print out parent, and so now we'll always get child parent. Okay, let's see. So here's an example of using execve. So we use execve. What we're doing is we're running ls. So ls being the great Unix program that lists the files in your current directory. So we give in, this is the path to ls, this is where ls is stored, and we're putting in the -l flag as a command line argument to it. Okay, and so then the question is, when we do execve, on this child, will the child ever reach this below the execve? Will that ever happen? Any ideas? Yeah?
No.
No, okay. So, yeah, that would be the normal case. What if execve fails? Then yes, yeah. So as long as everything goes great with execve, it'll never reach there. The only case that execve returns is when there's an issue. So we can and we can find that by, so I think it's man 2. We can see that by looking at the man page for execve. It tells us what it does. So it'll tell us what happens if it fails. But in the normal case, we never go below that. If we had code down there, it wouldn't ever get executed. So this is a way to make ls happen, and then the parent continues on doing whatever it was doing. Okay, so this is sort of a depiction of the hierarchy of the processes. So the process that's sort of the parent of all of the other interesting stuff is init, which has process ID 1. So and that's why init is responsible for reaping anyone whose parent is already dead, is because init is an ancestor of everyone that's running. And then init also, so init gets stuff that's running in the background, sort of your system stuff that makes your computer work. And it's also running the shell, and then your shell has all of the stuff you're running and anything that those things are running. This is sort of a simplified picture, assuming you're just doing a command line computer. This doesn't include what would happen if you have like a display manager and all sorts of stuff. But this is all you need to be able to, this is sort of the part you'll be working with Shell Lab, is the shell, and then children and potentially grandchildren and such. So signals. So we need some mechanism for passing around this information from to the processes that these things happened for this exceptional control flow. So the things that we have are signals, and they're really just numbers, but they're numbers that each one is assigned to a particular meaning of this is what happened. So so we can send these signals as from processes to other processes, and the kernel will do that, and then we can handle them. So some ones that you might have seen before, there's a sig interrupt. That's what you get when you do a control C, which the default action is just terminate the program. You've got sig kill, which is a stronger version, which says terminate the program, and you can't do anything to override or ignore this one. So sigint, you can write a handler that says do something else with it. Sig kill, you can't do anything about it. When you get that, it's going to kill it. You've got the seg fault, so you've seen that one. Sig alarm is when a timer signal happens, or sig child. So sig child will be sent as the signal to a parent when its child is stopped or terminated. And the default action is actually just do nothing with that one. But you can write a handler for it so that you can actually then do something when a child changes state.
What is the difference between an exception and a signal?
So let's see. So signal. So the exceptions, let's go all the way back. So we had these exceptions which were sort of called, these exceptions were caused by like hardware in the asynchronous case, or as the result of executing a particular instruction in these synchronous cases. In a signal, it's something that's actually not coming from the process executing an instruction, but it was sent to it by something else. So by another process, for instance. So like a asynchronous, a hardware exception would be like when a read-or-write event happens to a disk, whereas a signal would be one process is sending a signal to another.
But the segmentation violation, the sig-seg read,
Mm-hmm.
wouldn't that be the same thing as the fault, the unprotected,
The protection fault?
Yeah.
Yeah. So let's see. So protection fault. Yeah, I'm actually not sure of the exact relationship between them, but it might be that the protection fault generates a sig-seg v or something. Yeah, I'd have to check, but they're similar. I'm not sure of the exact relationship. Okay, yeah. So the kernel is what's in charge of sending these. So the kernel, of course, is the sort of the control unit of the operating system that manages all of these processes. And it's able to send a signal to a process just by updating some state that it's keeping track of for that process. And, it can happen for, whatever reason. Right. And so then a process can receive a signal. So one important thing about signals is that signals don't keep account of how many of that signal have been received. It's not like you have a list of I've received 5 sig kills. What you get is the signal has been received and we haven't done anything with it, or there is no signal. And so it's just, it's a true or false for every signal. If we send it multiple times before anything is done with it, the fact that we sent it multiple times is thrown away. We only know that it has been sent at least once. So signals are received at a context switch. So the time that signals are actually dealt with is when the process is changing context from one to another. They don't get dealt with immediately when they're sent. So it's sort of just every time we switch a context, we check and say, hey, are there signals to deal with right now? And there's 3 things we can do with it. We can ignore it. It's easy enough. We can just kill the process, or we can have our own handlers that we write and catch the signal and do something with it. And so, this is sort of the software version of handling hardware exception, asynchronous interrupts. Let's see. Yeah, so we can block signals. So there's a function called sigprocmask that will allow us to just ignore signals and say we don't care about them. If we want to run some code that shouldn't ever be interrupted, we can wait until we get a particular signal with sigsuspend. So when we call sigsuspend, what it'll do is it just won't continue executing that process until that signal is received. The kernel will start it up again once it gets that signal. And this is good because this allows us, it would be a bad idea to wait for a signal by doing something like having a loop that just continually checks if that signal has been received or something weird. Because that would be really expensive. It'd also be a bad idea to just tell the program to sleep for a couple seconds and then check if it's been received and then sleep for another couple seconds. Because then you're sort of not necessarily handling it when it happens, and you end up with race conditions and it's slow, and that's really bad too. So you shouldn't do either of those for your shell lab. If you think of those things, don't do them. Sigsuspend is the way you should be handling if you want your process to just not do anything until it gets a specific signal. You get to a point where you're just like, now I want to wait for sigchild. Then you should use sigsuspend and wait for sigchild with that, and then you'll start up once you get that. And you can't modify the behavior of sigkill and sigstop. So those are particular signals, and you can't write a handler for them that does something else. Sigkill and sigstop will do they'll kill your program, and you can't do anything about it. Which is good, because otherwise you could write a program that just ignores all signals and never dies. And that would be unfortunate if there was no way to kill the program, because then what do? You have to reboot the whole computer to get it to stop. So signal handlers, you can write your own handler for a particular signal. It's separate of the flow of control in the same process. So sort of when a signal handler happens, you go and you execute it, and then you continue back where you were, executing the process before the signal handler happened. And you sort of jump out, do this thing, and then jump back to where you were before. And it can be called anytime when the signal is fired. Okay. So here's what I said. Don't use sigsuspend when that's what you want to use. Don't do something else. So you can't use wait twice in order to wait for a signal. Sigsuspend is what you want there. Let's see. So you can read the details of this in the man page. I want to get to the shell lab stuff still. And every process, so we've got process groups. So every process belongs to a process group, and when we fork, we stay in the same group as the parent. So, and then you can change the group, but by default we just stay in the same group as the parent, and that will be something you'll do in shell lab. Let's see. So what do we have here? We had a job. Move a job. Okay. So here we have some code. We fork. The parent adds a job to a list of jobs that this child exists. And then when the child exits, it's supposed to remove itself from the job list. That's what this is doing over here. So when it exits, it'll remove itself. The parent is supposed to add it. But what's the potential problem with this, based on what we know about fork? Yeah.
The exec feed, or the child could run its exec feed before add job happens, and then the child will attempt to remove itself from the job list before it's been added.
Right. Yeah. Depending on the order these happen in, we might actually have the child removing itself before it gets added. So it removes itself, and maybe that causes bad things to happen because it's not actually in there. Or maybe it succeeds and then we add it and then it will never get removed because it's never going to return again because it's already done. So we want to sort of block signals in this code to guarantee that we won't be adding it at the wrong time. So we can block SIG_child, unblock it, and unblock it after the add job. So, of course, since we're forking, depending on which one we go into, we'll want to be able to unblock it in both. But the idea is that we make sure that we have SIG_child blocked before the add job, and we don't unblock it until after. So that way, if the SIG_child actually happens, we'll make sure that we have added the job before we've removed it. Okay, so now let's talk about Shell Lab for a bit. So Shell Lab is out. It's due Tuesday, November 3rd, so that's a week from tomorrow, right? And we've given you quite a bit of code already, more code than we've ever given you before, and it implements a lot of the boring stuff that will be helpful to you. So there's a lot of stuff in terms of like just managing the list of jobs. What you're writing is a shell. You're writing a shell, you'll, just like, a normal Linux shell, and you'll be able to put commands on it, and it'll run the program. And, you'll be able to run arbitrarily many programs in the background at once, and up to one program in the foreground at once, sort of like just like a normal shell works. And, you'll have a list of jobs of all the things that are currently running, and we've given you a lot of the stuff that handles that list of jobs and all that, because that's boring. But don't be afraid to write your own helper functions. In fact, you probably should be writing your own helper functions. In addition to the stuff we gave you, don't try to just shove the rest of it in main. It'll end up being longer than Cache Lab, for sure. So you'll want to make sure that you factor it well. So you'll want to be reading man pages and reading in your textbook about these different system functions. A lot of this lab is just understanding how these system functions work and where you're supposed, what they do, and how to, picking the right one based on what you want to happen at different points in your program. So these are all ones that will be useful to you, listed here. So you should make sure, you've read the man pages, read the appropriate part of the book that deals with all of these, and that you know how they work, so that you can use them properly. Don't use sleep to solve synchronization issues. So sleep is a function that just, and we can look it up. Sleep, that's not the one we want. We want this one, yeah. So sleep just makes your process stop running for some number of seconds, and it starts running again. One of the things that can happen in this lab is you have issues where, maybe you've removed a child before you've added it. The proper way to fix that is not to make the parent just sleep for 10 seconds before it, or make the child sleep for 10 seconds before it runs, and then hope that in those 10 seconds it gets added. Because, first of all, that's going to make your program really slow. Because now it's going to have to wait that amount of time to do anything, even if it's like something that's really fast. And also that's actually not correct in terms of fixing the issue, because if something still takes longer than that, then it still is a problem. Like you haven't fixed it, you've said hopefully it'll happen faster than this, but it might not. And so that's it's incorrect, and it's slow, and there is a way to do it. And so you should think about how to use signal masks and sig suspend or whatever is appropriate in the case to actually make things happen at the right time. And our grading code also forces things to happen in different orders so that we can test to make sure that you will do it right in the different orders. So some hazards is these race conditions. So race conditions, that's the name for these issues where things can happen in multiple orders, and the order it happens in actually makes a difference in terms of the correctness of the code, or the final result of the code. So you should, you want to write your code so that there are no race conditions. You should write it so that anything that can happen in an arbitrary order can happen in any of those orders, and it will still be a correct result. It doesn't matter if the child or the parent executes first. Either way, it'll still be correct. You need to make sure that you deal with the zombies. Don't have zombies just sitting around. You need to make sure that you, every time when the children die, you take care of them properly. You handle those signals correctly. And also, when you're running a foreground job, of course, your shell cannot be used to type in new commands until that foreground job is over. So you should think carefully about what the right way to make the shell not do anything more until that foreground job ends is. Okay, so let's go through some of the actual handout. Hopefully you can all see that. So I've untarred a copy of the handout over here. So this is what it sort of looks like. There's a lot of stuff. So what we initially give you is this tsh.c file. So this is, your starter code, and we've defined a lot for you. Like I said, we've got all of this. We've got some structs defined for you. We've got the headers for a couple functions defined for you. And then, we've got all of this is implemented way down here. And this is all sort of stuff to manage the jobs. And then some of these are empty, and you'll have to fill them out. And stuff to manage jobs. So you should start by reading through that and understanding what we gave you, and understanding what parts you still have to implement, so that you know exactly what you're doing. But as you go along, what you'll do is you write some part of your shell, and then you make. So this is same as normal. And what that'll do is that gives you a whole bunch of additional new things. So it's compiled a bunch of programs, and these are sort of programs to test your shell out with. And then it's also compiled a couple things called run trace and sDriver. So these are what you'll be using to test as you go. And we also have a reference shell. So we've got your shell, the reference shell, and 2 test programs. So we can run the reference shell. This is actually really useful if you just want to sort of see, what should the shell do when I do a particular thing. You can run the reference shell, and it will, you should be matching it with yours. So maybe I'm going to run ls with the reference shell, and hey, look, it prints out everything in the directory. And then, I can quit. If I run my own shell, then I can say, okay, what does mine do when I do bin ls? Well, it does absolutely nothing. Okay, that's great. So I know I have to update that. Yeah, I better handle being able to run programs from my shell. What does it do when I quit? It does absolutely nothing. So far, this shell isn't very good. There's stuff that needs to be implemented still. How do I get out of it? Okay, I can use Control D to get out of it. At least that works. Control D. Okay. Control C was completely unhandled too. You can see it just printed out "C". Okay, so we want to sort of go through and figure out now, what should I do first? And you should do things in the order of the traces. So we've given you a bunch of trace files. They're numbered 0 through 24. And what a trace file is it has in it a list of commands that's going to be passed into your shell, and it's going to run it on your shell and run it on the reference shell and make sure that they did the same thing. This one is an empty list. These lines starting with pound signs are just comments. This one just says if you give your shell just an end of file, does it actually just stop running? Which at least this one does. But then you can work up more to sort of more complicated ones, and now it's going to start running programs and stuff, and it's going to make sure that sort of your program is able to run a job in the background. This one's going to run MySpin in the background. Okay, so how do we go about doing this? So as we're going, we'll want to be able to run a particular trace on our shell and make sure that it's working on it. So there's this program run trace. You can see the information on it with the -h flag. And all you need to do, I'll put that up again. So run trace, we'll say, okay, let's run trace05.txt, and let's run on our shell tshell. So this is our shell. And what happens? Well, okay, looks like it just timed out. Okay, so my shell cannot run that one appropriately. But if I did run trace05, and gave it the reference shell, then it would print out this. So this is a way to actually run the trace files, see what the reference shell does, see what your shell does, and you'll want them to be the same. So you should work through the trace files. You should work through them in order, pretty much, because most of them depend on the previous ones working to be able to work themselves. They sort of add things that they're testing. Particularly, I think it's Trace02. Yeah, Trace02. You need to get Trace02 working before you can get any of the other ones working, because all of the ones 3 and after rely on Trace2 being correct. But you can work through them with run trace, sort of trying it out on the reference shell and trying it out on your own and seeing how it happens. You've got a flag -v that'll give you even more information if you want more information about what's going on. So now this is sort of printing out what's happening to the job list and what's happening with signals. And so, you can go through this on the reference shell. That's really useful if you're not sure why yours is not doing the right thing. You can see what the reference shell did when it traced through it, and then check if yours is exhibiting similar behavior. And maybe you can see that they differ in some spot, and that's why it's wrong. Okay, and then once you've used run trace, and you see that you're passing some traces, you can use sdriver. So sdriver is then the actual grading script, and we can check sort of what it takes. It'll run it on all of the traces by default, and it'll run it 3 times by default. We can, I'm not going to run it on all of the traces because it's just going to do a bunch of failing and complain a lot because my shell is not implemented yet. But we could run it on a particular trace. So we could use -t and then say, okay, I just want to run it on trace 5. We already know that one doesn't work. But it'll print out the fact that, okay, so what did mine do? What did the reference one do? What was the difference between them? And so the difference is that mine complained that it timed out, and the reference shell did not do the same thing. And then, like 0 out of 1. So run trace is the way that you do particular traces. And then once you've got those working, you can run sdriver to sort of check that that's just going to run them all. And then, it is really actually a good idea to just sort of use the reference shell. And you can actually have the reference shell print out additional information. So reference shell with -v will print out additional information as you go. So it's actually one of the best ways to start, even before you're passing traces, is to sort of just run a program in the reference shell that does whatever you want to do with your trace, and sort of see the details of what the reference shell is doing, because you want to be doing the same thing. So, and then one important detail is that these process IDs, so every process has a process ID associated with it in the system. These are not unique. They're different every time. So here it was 22463, and now it's 22494. Those will be different. And the grader, of course, will ignores the fact that the process IDs are different. Other than the process IDs, though, you should be exhibiting the same behavior as the reference shell. So, and then we can, when we edit our shell and we open up the file, we change it, then we can make again and compile the new version to try out our tools on it some more. So any questions about the programs for Shell Lab, how to run it, the stuff we talked about? Yeah?
If we want to use the fork wrapper,
Mm-hmm.
we can download the CSF.h.
Yeah. You can use the stuff from the website. Yeah, that's all.
When we upload to AutoLab, it will know. It will crash.
Yeah. So as long as it's included in the tar. So actually, I want to see. Yeah. So as long as it's included in the tar, it will be fine.
Do we have to be able to handle background in the built-ins, or the built-ins not background by definition just because they're like functions that are?
Yeah. So the built-ins you can't background. So we can run the reference, and if we do like quit and try to background it, it actually it does quit. Interesting. Let's get it to print out some more information and see what happens. So if we do quit and we try to background it, it just quits without printing out anything more. Okay, so maybe you do have to do that. So let's see. So there's another one, jobs. I guess we don't have any jobs. We did jobs, background it. Okay, well. You can play around with the reference compiler and just match that is the best reference.